presentation, we will cover the following topics. Describe a time series. Describe the time series algorithm. Select the best uses for the time series algorithm. Explain the uses of ArtXP and ARIMA. And describe the input data required for the time series model. A time series consists of a series of data collected over successive increments of time or another sequence indicator. These can be things such as the closing price of a stock on a daily basis, the monthly sales volume of a product, or the distance from a set location at an equal interval, such as how far you are from your home every 5 minutes. Any sequence of numbers that are recorded over a time, regardless of how trivial, forms a time series. The time series is commonly used in forecasting. It is the development of data mining models to predict future values based on previously observed values. The time series data mining model is rather particular in its needs. Each time series within a mining model must contain one key column. This key column specifies the time slices. It can be any data type, but it is usually a numeric data type. It must also contain a predictable column or columns. These columns must contain continuous numeric values with no missing data points. Within one of the time series algorithms, it is possible to use cross-prediction. Therefore, the column can be defined as input or predict to allow cross-series prediction. The training data must be clean, representative, and ordered chronologically. The time series data must not have any missing data points. The time series mining models have characteristics that differentiate them from other types of mining models. The models can be trained on small data sets. What is needed is a data set that is large enough to show any cycles or seasonality. The training data must be loaded in chronological order. The mining model can be ephemeral or short-lived. That means that predicted values become obsolete once the particular time that is being forecast has passed. Models may require reprocessing as new time data becomes available. The models must be configured with drill-through enabled. We do not use holdout cases for accuracy testing when creating a time series model. A model is defined in terms of an algorithm that is responsible for detecting patterns. You have inputs and outputs. In a time series, your inputs are going to be sequences of time and snapshots like sales value that occurred each month. When we process the model, that means taking carefully prepared data, like our sales history, passing it through the data mining engine that is responsible for detecting and then storing the patterns in the model. The Microsoft time series algorithm was first delivered in Analysis Services in 2005. At that time, it used a single auto-regressive time series method named ArtXP, which means auto-regressive tree with cross-prediction. Since 2008, the time series algorithm now provides the blending of two machine learning algorithms for forecasting continuous values. This includes values such as stock prices, sales, or temperatures. The algorithm is designed to detect trends within the data. It uses these detected trends to predict the future steps in a time series. We can specify an algorithm to use within the mining model, or we can use the default. ArtXP, which we learned earlier means auto-regressive tree with cross-prediction, is the preferred algorithm for short-term prediction. ARIMA, which means auto-regressive integrated moving averages, is the preferred algorithm for a longer-term prediction. Within the Microsoft time series algorithm, these two algorithms are blended. The Microsoft time series algorithm, using the mixed model, works by using only ArtXP for making the first couple of predictions and combining ArtXP and ARIMA in such a manner that the weighting becomes more heavily on ARIMA until ArtXP is no longer used. We have the ability to control the rate at which ArtXP is decreased and the rate in which ARIMA is increased by setting the prediction smoothing parameter within the algorithm parameters. We will not be covering prediction smoothing in this particular module. The first of the two algorithms is ART-XP, autoregressive tree with cross-series prediction. This was the first algorithm that was delivered in 2005. What's great about this algorithm is the cross-prediction capability. That's where you have multiple series that could in fact show influence across them. For example, as the sale of chocolate ice cream goes up, strawberry ice cream sales may go down. It may detect patterns between the series themselves. This concept is unique to Microsoft's implementation of the autoregressive tree. It's considered to be a reasonably accurate algorithm for short-term prediction. The way that it works is it uses past steps when it predicts the next step. In the next step, it may start using predictive steps, so it's predicting based on predictions. It can very quickly become unstable, so we use it typically for short term. In this image, I'm using only ART-XP. I've turned on Show Deviations. These are the vertical lines that you see near the right side of the chart. I'm predicting out 15 steps, 15 days in this case. You can see that as we move into a longer-term prediction, the prediction line flattens out and the deviation becomes larger. The larger the deviation, the more unstable and less reliable the prediction. The ARIMA algorithm, or autoregressive integrated moving averages, was introduced in analysis services in 2008. It has become an industry standard forecasting algorithm. It is considered more accurate and stable for long-term predictions. However, it does not support cross-series prediction. In this image, I'm using only ARIMA. I've turned on Show Deviations. These are the vertical lines that you see near the right side of the chart. I'm predicting out 15 steps, 15 days in this case. You can see that as we move into a longer-term prediction, the prediction line continues to show a pattern and the deviation does not increase as rapidly as we saw with ART-XP. Again, the larger the deviation, the more unstable and less reliable the prediction. We can see that these predictions are more stable. In this image, I am using Mixed, the algorithm default. I've turned on Show Deviations. These are the vertical lines that you see near the right side of the chart. I'm predicting out 15 steps, 15 days in this case. You can see that as we move into a longer-term prediction, the prediction line continues to show a pattern, and the deviation does increase slightly more rapidly than we saw in the previous slide using only ARIMA, and not as rapidly as we saw with ART-XP. Again, the larger the deviation, the more unstable and less reliable the prediction. We can see that these predictions deviate more rapidly and then quickly become more stable. We will review the data required for the time series model. We looked at these requirements earlier and noted that we need a single key time column. That is, each model must contain one numeric or date column that is used as the case series, which defines the time slices the model will use. The model requires a predictable column. That is, each model must contain at least one predictable column around which the algorithm will build the time series model. The data type of the predictable column must have continuous values. An optional key series column can be added. That means each model can have an additional key column that contains values you need to identify a series. We can customize the Microsoft time series algorithm. For our purposes here, we're only going to look at periodicity or seasonality. The algorithm is designed to detect seasonality. In many cases, the algorithm detects seasonality better than someone who is not specifically trained in the field in which we are doing the analysis. Both algorithms support the detection of seasonality or periodicity. Analysis Services uses what's called a fast Fourier transformation to detect seasonality before training the model. We can affect the seasonality detection and the results of the time series analysis by setting algorithm parameters. We do this through setting a value or multiple values for the periodicity hint. We can provide the algorithm with additional information about expected cycles in the data, and we can potentially increase the accuracy of detection. Again, the algorithms are very sensitive to seasonality. Hence, providing the wrong hint can adversely affect the results.